And now let me turn to, well, it's supposed to be hour 2. We're running a little behind, but that's okay. Okay, so to kind of, we've gone through a lot of concepts and we've learned a lot of things. So I'm going to take a kind of a quick breather and talk about maybe a situation that might resonate with a lot of you. So, let's imagine that we have the Zoom call between our protagonists, Alice and Bob. So, it's Bob's birthday and Alice says, "Happy birthday, Bob." Thanks, Alice. You're muted. Oh, sorry. Thanks, Alice. Well, I've got a gift for you. Oh, that's very nice of you. There's a problem, though. It's a qubit. Oh, not to worry. I have a quantum computer here. Just tell me the amplitudes of this qubit and I'll make it myself, says Bob. Well, here's a problem. The amplitudes are transcendental numbers. There's infinitely many digits in these amplitudes. So I don't think our Zoom call can last long enough for me to tell you all these amplitude digits. Because, and then Bob says, yeah, we only have the free version of Zoom, which only lasts 45 minutes. So it seems like we're kind of in a trouble here. But do you still have half of the EPR pair that I gave you in person before the pandemic? I do, in fact. Well, that seems like such a long time ago. Then there's a way I can get your gift qubit. Okay, so that's the setup. This brings us to quantum teleportation. All right. We have Alice and Bob. Alice really wants to send a birthday gift, this birthday qubit, to Bob, but they're only connected via this classical communication channel, which is this Zoom call, 45-minute Zoom call. But it so happens that they, in addition to this gift qubit that Alice has, they share this EPR pair, which they prepared ahead of time. And quantum teleportation is a protocol that allows them to make use of these resources for Alice to send this state psi to Bob, no matter what alpha and beta are. This works for arbitrary quantum state psi. So here's a protocol, and this is our first introduction to quantum circuits. And I'll slowly explain what this picture means if you haven't seen it before. So in this is a description of a quantum computation that Alice and Bob will jointly perform together. And so here, these horizontal wires correspond to a different qubit. So there's 3 qubits in the setup. There's the gift qubit, and there's the 2 qubits that form this EPR pair. We read the circuit from left to right. Time runs from left to right. So at the beginning of this protocol, this describes the state of their 3 qubits. Alice's state is in the state psi, and they share this EPR pair. Okay, okay, good. So that's how it starts off with, and then each of these elements, or sorry, these first 2 elements will describe unitaries, right? That Alice is going to apply on her 2 qubits. So Alice has this psi and this qubit of the EPR pair. She's going to apply this unitary. This is a C0 gate. And this black dot indicates this is the target qubit. Sorry, not the target. This is the control qubit. And this is the target qubit. And then after the C0, she's going to apply a Hadamard, right, which is this matrix we've seen before. After she's applied these unitaries, which she can do on her side without Bob having to do anything, then she's going to measure both her qubits. She gets 2 bits out, A and B. And these are classical bits, these outcomes. They're probabilistic, but using the Zoom call, she can send over these 2 bits A and B to Bob, who can then, on his qubit, he can apply these quantum unitaries, these gates, this x and z. So what is this? Sorry, I think I might have switched around the A and B. So this is z to the A and x to the B. So x is this bit flip unitary, which we saw before. Z is another unitary. It looks like this. It's called the phase flip unitary. And basically the exponents A and B mean whether to apply the unitaries or not. So let's say that A and B happen to both be 0, then Bob actually doesn't do anything to his qubit, right? And if that's the case, then the claim is that Bob will then have the gift qubit. But if A and B are different from 0, then Bob has to perform these corrections, right? So for example, if A is equal to 0, but B is equal to 1, then Bob has to apply the bit flip unitary, but not the phase flip unitary. Okay, so hopefully the description of the protocol should be clear. And I claim that no matter what, in all cases, no matter what outcomes Alice gets for A and B, at the end of the protocol, Bob is going to have the gift qubit. Okay, so let's just run through a couple cases, and then you can sort of work out the rest yourself. So let's say, well, actually, before that, let me say, how do we analyze these quantum circuits? Well, basically, you just sort of analyze the state of the circuit, instant by instant. So in the beginning, the state that they start with is in psi tensor this EPR state. And let me write out what that is. So we can expand what all these states are. This is alpha ket 0 plus beta 1. That's the state psi, tensor 0, 0 plus 1, 1. Okay, and let's just expand this out because that'll be useful for us. So if we expand this out, then we get a description of a 3-qubit state. We get 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. Okay, so that's the state they have. Okay, so let's look at what happens. You know what? I'm gonna move this over just so I have more space. Okay. So after the C0 gate, let's see what happens. Well, we just apply the C0 gate to all of the terms. So this is going to be 1 over square root 2 alpha 0, 0, 0, because applying the C0 to the first 2 qubits of 0, 0, 0 doesn't change anything, plus alpha 0, 1, 1, right? Again, nothing's changed because the control qubit is still in the state 0. We have beta, we have 1, 1, 0. So it's, the second qubit's been flipped because of the C0, and now we have beta 1, 0, 1. All right, so that's after the C0, and now let's compute what happens after we apply the Hadamard. So we just now apply a Hadamard to the first qubit again. So then we get 1 over square root 2 alpha. The 0 state turns into the plus state. Alpha plus 1, 1 plus beta. And the 1 state turns into a minus state. 0, 1. Okay. So that's the state of the system after the Hadamard. All right, let me copy this so I can use it for the next page. Okay, and we're going to measure it. So to really figure out what we have, we should write everything out in the standard basis. And so if you do the math, sort of, you do all the algebra, you sort of expand everything out, you should get 1/2, and then let's see here. Well, there turns out to be a lot of terms, but let's see. Okay, so actually, before we do that, let's imagine it, in the following way. So this state, this is the state of the system at this point right here. Okay, that's the state of the system. And then we're going to measure both qubits, both of the first 2 qubits. So, this first qubit and the second qubit. And let's say we measure, we measure the second qubit. Since these 2 measurements are happening simultaneously, it doesn't really matter which order where we consider the measurements happening. So let's imagine we measure the second qubit first, right? This B qubit. All right. Then, suppose B turns out to be, I don't know, let's say 1. Okay. Well, then, we have to remember how our partial measurement rules worked. So we just have to look at all the cases where the second qubit is in the state 1. So the state collapses 2, and we're going to write down the unnormalized one. So I'll sort of leave off the normalization. We have plus alpha plus 1, 1 plus beta minus 1, 0, right? And then all the other terms go away. And okay, so that's after we measure the second qubit and we have this collapse. What happens when we measure the first qubit? Okay, so this state is now much easier to, we have fewer terms, so we can actually write out what it is in the standard basis. So this is, up to normalization, this is 1 over square root 2. This is alpha 0, 1, 1 plus beta 0, 1, 0 plus alpha 1, 1, 1 minus beta 1, 1, 0. Okay, so now we're going to measure the second qubit, or sorry, measure the first qubit. And suppose A happened to be, I don't know, 0, right? That was the outcome that we got. Okay, then again, it collapses to, we just delete all the terms that are not consistent with that. We get, alpha 0, 1, 1 plus beta 0, 1, 0. Okay. And so now we're done. So we have our, well, almost done. So we have our, let's refactor the state. So this is equal to 0, tensor 1. Those are the state of the first 2 qubits. tensor alpha 1 plus beta 0, right? So this describes the state of the system after the measurements, but before Bob has applied his corrections. So this corresponds to this state. All right, so in the case A equals 0, B equals to 1, state after the measurement is 0, comma 1, tensor alpha 1 plus beta 0. And this looks, almost correct. Like Bob has the almost the correct qubit, except the alpha and beta are switched, right? The alpha should be with the 0 state and the beta should be with the 1 state. And that's why he needs to do these corrections. So when Alice sends over these two bits, A equals 0, B equals to 1, over the classical communication channel, Bob will then know to apply the bit flip operator, right? So he'll apply X to the B, and he won't apply Z. So Bob applies X to his qubit, right? And remember that this bit flip operator switches 0 and 1, which is exactly what we wanted. Bob's qubit is in the state alpha 0 plus beta 1, right? Which is exactly the GIF qubit that Alice wanted to send. So this is just one particular case. You can work through the other 3 cases and see that in each case, the corrections will be exactly what's needed for them to carry out this protocol and for Bob to get the gift qubit. Okay, so I won't go through the other cases. You can work it out on your own. But one key thing to note is that this protocol seems really cool, but it does not allow Alice to instantaneously send over the state psi to Bob, right? They really need this communication channel, this classical communication channel, in order for this protocol to work. She needs to send these 2 classical bits, A and B, over. And if Bob didn't receive these 2 classical bits, A and B, then what he has, there's no way for him to recover this qubit psi. From his point of view, it just looks like a completely random qubit. And we'll actually make this more formal when we talk about mixed states in just a little bit. But yeah, this classical communication is necessary. Okay, so that's quantum teleportation. This is the first quantum circuit that we've talked about. And it really takes advantage of quantum entanglement as a resource in order to do this transference of psi. All right, so you can imagine finishing up this little movie. She's going to apply her gates. She tells Bob what measurement outcomes she gets. Bob will apply his corrections, and he gets his qubit, and he's happy. Okay, so that's quantum teleportation. Now let's turn to the quantum circuit model. Okay, so we've basically have a good picture of what a quantum circuit looks like. It's just a bunch of gates acting on different subsets of qubits, and we can have measurements in them. More generally, quantum gates, they're just unitaries. And here I'm just writing down a list of common gates that come up in quantum computing. There's the bit flip gate that we saw. There's the Hadamard. And there's these phase gates. Phase gates basically, what do they do? On the 1 state, they apply some phase, some root of unity in front. So the Z gate will put a -1 in front of the 1 state. This thing called the P gate, which is the phase gate, applies an I, a 4th root of unity. And this thing called the T gate will apply some other root of unity, this 8th root of unity. And they always leave the 0 state alone. Okay. So those are some some very important single qubit gates that come up again. And the most important 2-qubit gate that we'll use is the C0 gate, which we've seen. All right. So quantum circuits, you have these wires, you have these qubits, and then you just apply gates to different subsets of them in some sequence. And generally speaking, even though like before we could have intermediate measurements, we'll typically save all the measurements for the very end of the circuit, okay, just to keep things simple. And so what that means is, we can think of a circuit as specifying you're going to apply a sequence of unitaries. So the first part of the circuit is unitary evolution, and then you measure at the very end. So at the end of the computation, you'll have some general n-qubit quantum state. And when you measure, let's say, all the qubits, you're going to get some n-bit string with a probability that's related to the amplitude in this way. All right, so let's talk about universal and non-universal gate sets. So I've described to you, what a quantum circuit is. It turns out that, if you have a quantum circuit consisting of 1 and 2 qubit gates, this is universal for quantum computation in the sense that you can implement any possible unitary you like. So if you have an n-qubit unitary U, you can build a circuit to implement it out of these gates. But in the worst case, any such circuit will require an exponential number of gates. And not only that, but really to get this general unitary down, you'll need to use arbitrary single qubit gates G. But as long as you're allowed to do that, you can't implement any unitary you like. But in practice, we can't use any possible single qubit unitary. We only get to use gates from some finite gate set. You can imagine it's like the instruction set of your quantum computer. So let's just talk about finite gate sets. A universal gate set is one where just by using gates from this set lambda, you can approximate arbitrarily well any unitary you like. So this set lambda is a universal one. If someone walks up to you with this unitary U, then you can break it down into a circuit consisting only of gates from this gate set, and you can approximate this unitary U arbitrarily well. And by notion of approximation here, we just mean that if you plug in any input vector into either the ideal unitary versus the circuit that you built, the difference in the output state will only differ by epsilon. Okay, so what are examples of universal gate sets? There's many. People come up with all sorts of different universal gate sets. Here's maybe the most important one for this winter school. This gate set, which is called Clifford plus the T gate. Okay, this is a universal gate set. What's Clifford? It's a very important subset of unitaries that are generated by this Hadamard P gate, this phase gate, and the C0. So these Clifford gates include all of the following, right? The Clifford gates form a group, but they're generated by HP and C0. Here's the unitaries are in here, and this T gate, this phase gate, is non-Clifford. And if you just add in this one non-Clifford gate, you get a universal gate set. Okay, let's talk about, just focus on the Clifford. So Cliffords they're not a universal gate set, but they have some really nice properties. They're not even universal for classical computation. So what's their use? Well, one important fact is that Clifford circuits can be efficiently simulated on classical computers, meaning that if you have a circuit that only have Clifford gates in them, and you start in the all zeros input, then the behavior of this computation can be simulated in polynomial time. This is called the Gottesman-Knil theorem. Um, and another important fact, and this is something that will come up later in this course, is that Clifford circuits have, can also be equivalently be defined in terms of the behavior on something called the Pauli matrices. So Pauli matrices, they're another subset of gates. It's an even smaller subclass than the Clifford gates. And they're generated, they're matrices that are generated by these simple unitaries, X and Z, right? You can consider tensor products of these Pauli matrices, right? So X and Z are single qubit unitaries, but if you have, X tensor X or X tensor Z, or tensor identity, and so on, these are all called Pauli matrices. And the interaction between Clifford gates and these Pauli matrices are very nice, and they'll be used. So what is the relationship? Let's say that you have a Pauli matrix, an n-qubit Pauli matrix that's a tensor product of individual Pauli matrices. So these W's will be, identity, X, Z, or X times Z. Those are all Pauli matrices. If you have an n-qubit Clifford circuit, then you can, if you first apply the Clifford circuit C, and then apply this Pauli unitary, that's the same thing as applying a Pauli unitary, maybe a different one, followed by the Clifford circuit. So another way of saying it is that Clifford circuits map Paulis to Paulis, right? So simple examples, let's just deal with the 1 qubit case for now. Let's say we have a Hadamard, which is a Clifford gate, but it's not a Pauli gate, times X. This is the same as the Hadamard moving, shifting over, but then you've changed the Pauli gate to a Z gate, for example. Another example is, let's say you have, let me draw it in circuit notation. Let's say that you have a circuit that looks like you apply a C naught, followed by an X gate. So here we're saying that time is moving from left to right. This is the same thing as applying the X gate, this is the same thing as applying the what does it turn out to be? Right. So this is the same thing as applying the X gate on both qubits, and then applying the C naught. Right. So this X tensor identity has now become X tensor X. Right. So this is the relationship between, this is one way of defining what Clifford unitaries are. Okay, and that will come up. All right, so we talked about universal gate sets. So now without lots of generality, you just assume that all the gates in your circuit just come from, say, Clifford and T. Let's talk about computing classical functions using quantum circuits. So let's say you have a classical function f, some Boolean function, maps n bits to m bits. How can you compute this using a quantum circuit? Well, we can call these classical functions as subroutines using classical oracles, right? So the reason we need to talk about these oracles is because this function f, it doesn't necessarily correspond to a unitary. F might not even be one-to-one. And so, but in quantum computations, everything has to be reversible, right? So we somehow have to encode things as unitaries. So the way to do that is, for every such Boolean function f, there's an associated unitary u sub f. It acts on n plus m qubits. And the way it behaves is, the first n qubits represents the inputs in the standard basis. And then we have this target register B that has some fixed value. And this unitary will just add the value of f of x into this target register. So this is bitwise XOR. All right. So just to give a simple example, let's say f is the AND function, so it maps 2 bits to 1 bit. So the classical oracle corresponding to this AND function, let's say we have bits A, B, and C. It leaves the first 2 bits alone, but then XORs the AND of A and B into this last register. Right? And then you can similarly compute what happens for the NOT gate. This NOT gate, if you think about it, this is something we've seen before. This is just the C NOT unitary. You can check that the way we've defined this actually is a unitary map, right? So this is a valid operation that can occur on qubits according to quantum information. So no matter what function you have. Okay, and so now that we have this classical oracle U sub f, we can just stick it into any quantum circuit we like, and this gives us a direct way of computing this function. For example, if you wanted to compute f of x, well, you initialize your qubits in the state x and this target register in the state 0, and what you get is x f of x, and then you have the value that you wanted. Okay. And another important thing is that this construction of this classical oracle is it's a reasonable thing, because if you had a size s classical circuit computing little f, then there's going to be essentially a size s quantum circuit computing this oracle. All right. But magic starts happening when we start evaluating these classical oracles, these unitaries, on superpositions of inputs. Okay. So let's talk about something called Deutsch's problem. This is a kind of illustrating example. Let's say you're given a very simple 1-bit function, f maps 1 bit to 1 bit, and you want to determine using one quantum query whether f of 0 is equals or not equals to f of 1. Classically, clearly, you would need to make 2 queries to this function, but quantumly, you only need to make 1 call to this this classical oracle to find out. And this is the quantum circuit that allows you to do this, to distinguish between these 2 cases. And here it makes just 1 call to the classical oracle. I won't go through the analysis. This is something that you can work on your own. But you can see it's like a very useful exercise if you haven't gone through it before, because you can see like how these negative amplitudes really come into play to help this quantum circuit distinguish between the 2 different cases. So let me skip past this. And in the last few minutes, let me talk about Grover search. Okay, so this is another quantum algorithm, and this solves the unstructured search problem. All right, so you're given in this problem, you're given black box access to a function f that maps n bits to 1 bit, and you want to find an x such that f of x is equal to 1. And if you're just given black box access to this function, classically you would need to make order 2 to the n queries to f in order to find such an x if there exists one. But the quantum query complexity is better by a quadratic factor. So the number of queries you need to make to this classical oracle U sub f will be square root 2 to the n. Okay. And here, actually, just to describe the algorithm in a kind of a nice way, we're going to call a slightly different oracle. It's not going to be this U sub f that we described before, but it's going to be another unitary that's equivalent, and it's called the phase oracle. So the way it works is it's an n-bit unitary, V sub f. It acts on classical basis states, x. And what it does is it leaves the basis state unchanged, but it puts a phase in front. And the phase will depend on the value of f of x. So it multiplies it by -1 to the f of x. And it's a different definition of oracle, but it turns out that the previous oracle, called an XOR oracle, and phase oracles, they're equivalent, right? You can construct a circuit going back and forth between the two. So you can do that. So we're going to just use this v sub f instead. And so here's the Grover search algorithm. For simplicity, we're going to assume that there's a unique string x star such that f of x star is equal to 1. This Grover search algorithm acts on n qubits that starts in the all 0 state. And then we're going to apply a tensor product of n Hadamard gates to, one Hadamard gate to each of the qubits. So we write that as h tensor n. And then we repeat a subroutine square root 2 to the n times, right? So it's going to be we're going to repeat this Grover iterate, which is we're going to apply the phase oracle and then some other unitary we call R, just over and over again. And at the very end, we're going to measure, and the claim is that with high probability, we're going to get this string x star. Okay, so let's analyze this, or let me give a brief sketch of how you analyze this, the circuit and show that it works. What happens when you apply n Hadamards to the 0 state? Well, each 0 gets turned into a plus. And if you write this out, this becomes the equal superposition of all n-bit strings. Okay, so that's going to be the state after these n Hadamards, and then we apply these Grover iterates over and over again. And I'm going to call the state S, right? So that's S for equal superposition. And V sub f is this phase oracle I mentioned. What is this R? So this R as a unitary is going to be this following funny looking matrix. It's 2 times the outer product of the state S with itself minus the identity. Okay. You can check that it's unitary. This is something you can verify. And it's something called the diffusion operator. Okay, so it looks a little abstract, but this unitary R, you can implement it using a small number of gates. Okay, don't worry so much about what it is now. But basically, the purpose of when you put together this Grover iterate is that the intermediate state of this algorithm will just lie in this 2-dimensional subspace between the starting state, this uniform superposition, and the desired target state x star. And in the beginning, it starts as S, but as you apply this Grover iterate over and over again, it's going to rotate closer and closer to x star. So after one Grover iterate, it's some vector like this. But after square root 2 to the n iterates, it'll be very close to x star. Okay, so we're at the end of the hour, but that's sort of just a cartoon picture of what this Grover search algorithm is doing. And then I'll say just a couple more words about it when we pick up in half an hour.